So this is very far from beautifully choreographed, but I have a handful of polarization demos to show you. And this will be the first one. In fact, actually, I'm going to start with a not polarization demo, just to kind of demonstrate what this thing is and how it's working. So this actually makes microwaves. So you may have seen these on old microwave towers for communication, these kind of bullhorn-shaped thingies. It's making 10.5 gigahertz microwaves, so that would be the frequency. And you can figure out the wavelength. That would be a very good practice problem. And this is the thing that detects microwaves. So the detection of microwaves shows up as current going through the circuitry of this. And I've put it on its maximum sensitivity. And if you can kind of tell from the top down is I've misaligned these, so the beam of microwaves is missing this. And then I'm going to take this piece of plastic, and I'm going to do something remarkable. Plop it right there, and all of a sudden we detect some microwaves. Take it off, we don't, they miss. So this is actually, as far as microwaves are concerned, a mirror. So, and you could work out the angles. You've got angles on there, totally consistent with the law of reflection. It works for microwave light, not like you didn't believe that. Okay, so now I'm going to turn the sensitivity down to like medium down. And I'm going to take these and align them 180 degrees away. So this is something that light doesn't naturally do, at least visible light, the stuff that you're used to. But we can engineer microwaves to do, which is one of the nice things about microwaves. So one thing I can do is I can demonstrate that this actually makes polarized light. So I don't know which direction, but let's just pretend, because this is the easy way to see me waving my hand. So what's known as a hand waving argument. So let's say that the microwaves are polarized in that direction, which would be the direction that the electric field is waving. And then let me turn this by 90 degrees. So that's actually detecting polarized microwaves, and that's creating polarized microwaves. And when they're lined up with the same polarization, you can see that increase. And then as I turn it, you can see it decrease. That's 90 degrees. That's 45 degrees, which is half-ish. And this should kind of go like cosine squared. So first, let's line them up. And let's do that in a different way. So as far as microwaves are concerned, which have, I'm sure you've all figured it out in your head that 10.5 gigahertz microwaves are a little bit, in the order of a centimeter big, so slightly less than. I can actually take this piece of metal, and what'll happen is if the electric fields are polarized with the metal, they'll be killed. So they'll try to make it through there, and the electrons will basically kill them off. So this is what I was saying about the icon. The polarizer icon actually would be the opposite direction of the slats on this, because the polarizer icon says these are the microwaves that I let through. But the way that actual physics works is these are the ones that I kill, because these are the directions that electrons can flow. This has absolutely no relevance for problem solving. You just got to remember that the icon tells you what gets through. And that has nothing to do with this, even though they look similar. Okay? So I'm pretty sure that the microwaves are polarized in such a way that they're being killed off by that light, or by electrons flowing in that direction. And if I turned it 90 degrees, maybe I can get them to come back. Sometimes it's a little bit finicky. You have to turn the sensitivity up a bit. Okay, so turns out I was wrong. I just had the sensitivity wrong. So now they're getting through, and now they're gone. So this is the polarizer killing them, as you can see from that. So polarized, non-visible light waves, pretty cool. So let's go back to visible light, and I asked you guys to puzzle through a weird situation where I killed all the light with two polarizers. And then what would happen if I put a third one back? So here is that demo, and we'll line you guys up looking straight down the barrel of the demo. And in case you don't remember, I have a light. And the light's pretty bright. And I killed the light with two cross-polarized polarizers. So I have one. So this thing creates unpolarized light. What I do with the first polarizer is I create polarized light. Let's just call it that direction. And then the second one, I can kill it all off. Right? And if I turn this so that they're parallel, I can get it back. If I turn it so that they're perpendicular, one polarizer this way, one polarizer that way, I can make it all go away cross-polarized. Okay, and then this is, in the 1980s, this was kind of expensive, but this is a piece of polarized sunglass. You can see it does nothing. And I'll put it inside. What's it going to do? Can't have less than 0, of course, so nothing happens, but of course you're wrong. So really bizarre. I get light actually showing up again if I did that right. Yep. And I'll turn it a full turn, and what you can see is light, dark, light, dark. So what on earth is going on with that? So what I would ask you guys to do, and we'll do this when we do a little bit of board work in a second, is draw the diagram and trust science. So I have 1, 2, 3 polarizers. For each one, figure out their action on the light that it gets, and then the after polarizer polarized light, so the stuff that comes out. And you'll see something kind of interesting and a little bit non-intuitive. So I want to show 2 more demos and then talk about natural polarizers, and then we'll do one last pretty crazy demo. So here's a carefully made, really expensive piece of demonstration technology, which is one of those old overhead projector things, and a bunch of pieces of packing tape put on it. And I will put it through there. And I'm not sure how well this is going to turn out, so I will zoom in. And then I'll rotate it. And so you can see something kind of neat happening, hopefully. So again, we're in this regime where I basically killed off all the light with 2 cross-polarized polarizers. And then here goes cellophane. I'll rotate it. And then I will do the same thing. This is a bottle of corn syrup. So corn syrup. And I'm going to put it in between the polarizers. And it's not going to be particularly impressive. And then I'm going to start rotating maybe the back polarizer, I think is the best one for this. Clearly, this is some sort of bizarre stunt corn syrup. So one might think that this has something to do with like the particular direction that I'm choosing. So let's make it super blue. Let me rotate the corn syrup. So what do you think is going to happen? Looks still pretty blue to me. Okay, maybe I was rotating it the wrong way. Let me rotate the corn syrup like that. What's going to happen? Okay, so chemistry people, what's dextrose? And what's glucose? And have you ever heard of L-glucose? So that has to do with this particular phenomenon. And I'll let you guys chew on that for a while. Don't worry, you won't be asked about circular polarization, but I just think this is like pretty neat. So we'll make it go through the color wheel one entire time again. So pretty awesome. Okay. So last like kind of theory topic in this, and then we'll have one more demo to show this off too. And you can be nostalgic for our old classrooms, is we were basically gifted. We gave ourselves these really neat polarizers, these Polaroid filters. So they're pretty neat. But you probably have seen weird mirage type stuff that was the action of natural polarizers, or you've had a friend who's paid a lot of money for sunglasses, or maybe you've done so yourself. So what's going on with that? So it turns out that nature itself polarizes a bit. And this is about all you need to remember from 1220 for the rest of this quarter. And it's not really that much. So here's water, for instance. Water's pretty good at doing this. And here's the sun, and we now know that the sun makes completely unpolarized light, which is what this like bristly thing up there means, right? What happens when water interacts with this light? What happens when water elects with, generically speaking, electricity? What do they tell you not to bring into the bathtub with you? Obviously, your toaster oven. And the reason is that water actually is like pretty electrically conductive and active. And so these two types of polarizations, the horizontal and the vertical, basically get treated differently. So there's the polarization that wants to make it into the water. Well, water doesn't like that. The water's got some free electron kind of activity and has something to say about that. And then there's the polarization that is going perpendicular to the surface, or perpendicular to the normal, or parallel to the surface. And water's kind of okay with that. So water basically doesn't like this sort of stuff. And because water, or electromagnetic waves wiggle really quickly, it will get all of the things that have an up-down component, whereas the left-right component basically do not get canceled. So it's not a complete cancellation, but it's a pretty severe diminution. So we'll say like complicated stuff, but water kills part of the electric field. So the part that's parallel to the normal. Okay, and then what's left over reflects and goes to your eyeball. So what is it that you want to buy, and what is it that you want to do with this to make yourself not see the glare coming off the water, if that's what you want to do? So what you want to do is you'd like to maybe see down and, like a fish there or something like that. If you're a fisherman, you probably use a lot of polarized sunglasses. So I want to cut out the reflection. What I can do is I can make a polarized lens, or I can make glasses out of two of them. And I got to figure out the right orientation. I've got to kill what's left over. So where do I put my polarizer? Like that or like that? Take a second, see if you can figure out what that is. Absolutely. My creepy disembodied eye will actually want to be polarized in such a way to kill everything that's left over. So that. Because what comes off of the water is, in a really extreme cartoon, something that would look like this, maybe. Right, the up-down part would get killed, and so I have a polarizer polarized like this. I can kill the rest of it. All the glare is gone at the cost of, not killing all the light. So one way of getting rid of the glare is to just, basically put a blindfold on, but we still want to be able to see stuff. So this is the idea behind polarized glasses and natural polarizers. Water's really good at this. Some other substances are pretty good. So I'll just write this. So this is all really complicated. This has to do with Maxwell's equations. But there is a thing called Brewster's angle. And the derivation is, again, complicated. But the thing it does is fairly straightforward. So there's a magical angle called Brewster's angle again, at which all of the parallel polarization is killed. So this is the angle at which all E parallel is removed. Okay, so what that would be for water, and these are the ratios of the indices of refraction, so exactly the things that go into Snell's law, which is why this, I think, shows up in textbooks, because it's like easy enough to be comprehensible or something. So really quickly, what is Brewster's angle for water? If you are somebody who wants to upsell sunglasses on your hunting and fishing website, what I would highly recommend you do is to go and find a picture of your glasses working and pose them exactly at Brewster's angle. So you want to put them at the place where, right at Brewster's angle, where all that's left is the polarized light, totally polarized light. Because then what you see is the reduction of glare is 100%. So also, on the flip side of that is when you're shopping for expensive sunglasses, realize that the images they show you in the catalog are probably taken exactly at Brewster's angle. So the way this would work is, no tricks. We're going from air to water. And, we'll use the average value for water. So theta P would be arctan 1.0003, 1.335 is about the average. And this is like 20-something degrees, 28 degrees, I think, for water. So let me look that up really quickly. Oh, it's 36.9. Good thing I looked that up. Okay. So let's actually see this in real life, because it turns out that there's a really great example of it in this building. Hi, this is Bannon Hall. You might remember me from such quarters as Winter Quarter 2020. And what we have is the lights and some beautifully cleaned and polished linoleum and the reflections of the lights. So this is initially where students might do Lab 2. And I have a polarizer. So what you're going to see is basically not a lot. So the polarizer will take unpolarized light coming from the overhead lights and cut it in half. So now what I'm going to do is, we now know that maybe the order of Brewster's angle might be like 40, 50 degrees or something. I'm going to come down here a little bit, and then I'm going to rotate stuff, and I'm going to start seeing this reflection polarization effect. And then down here, all the way at the bottom, I'm going to take this, it's at some random orientation, and then I'm going to start spinning the polarizer. And voila, I can make one of these reflections of a light completely disappear. And this is because that's the particular angle where the indices of refraction of the wax on the linoleum and air are matched such that all of the horizontal component of the electric field, that's the only part that makes it out of the reflection. So let me let this thing focus for a second. So the light comes out, all sorts of polarizations, bounces off of this spot, and the part of the electromagnetic field that was trying to go up-down into the wax on top of the linoleum, this part is killed, completely killed. All that's left is this, and then I'm going to put the polarizer in such a way that I kill what's left. So completely gone. So this is how you reduce glare off of the air-water interface if you're fishing, for instance. So right there, Brewster's angle.